By 1942, the Mosquito was supposed to survive daylight over Europe by pure speed. Then one German fighter became the standard day interceptor over occupied Western Europe. And after-action accounts stopped talking about clean escapes. They used a thinner word: outpace, accurate, and not enough. This is the aircraft that closed the Mosquito's daylight margin until the legal boost limit felt inadequate. The argument began in September 1939, when Geoffrey de Havilland wrote to Air Marshal Sir Wilfrid Freeman, the Air Council's member for research and development. The pitch was direct. We believe that we could produce a twin-engine bomber which would have a performance so outstanding that little defensive equipment would be needed. No gun turrets, no defensive armament, no rear gunner. An aerodynamically clean wooden airframe, 2 Merlin engines, and enough speed to render interception a losing proposition for any Luftwaffe fighter likely to appear. Freeman understood it immediately. He had flown DH-4s in the First World War, de Havilland aircraft, and knew the man behind the letter. He had also spent 2 decades watching conventional heavy bombers accumulate requirements that destroyed their performance: gun turrets, armor plate, multiple crew positions, the weight of their own protection growing until the aircraft could barely carry the protection, let alone a useful bomb load. The new design would reject all of that. 2 men seated side by side. Smooth wooden fuselage, no protrusions to catch the airflow. No defensive guns to complicate the external lines. The speed advantage that resulted wouldn't be marginal, it would be categorical. Freeman backed him. The AOC-in-C of Bomber Command at the time, Sir Edgar Ludlow Hewitt, wouldn't accept an unarmed bomber at all. He insisted the design at least be suitable for photographic reconnaissance. Ministry officials pushed for 2 forward and 2 rear machine guns, at minimum. Freeman got the defensive weapons requirement dropped regardless. On the 1st of January 1940, he chaired a meeting with de Havilland and John Buchanan from the Ministry of Aircraft Production, and a prototype was ordered under specification B1/40. A light bomber capable of 400 miles per hour at 24,000 feet, cruising at 325 miles per hour at 26,500 feet, service ceiling 32,000 feet. The crew would be 2. Lord Beaverbrook called the project Freeman's Folly. De Havilland built a mock-up with a gun turret aft of the cockpit to satisfy the skeptics, then made no other changes. The turret was theatre. The prototype, W4050, flew from the grass strip at Hatfield on the 25th of November 1940, piloted by Geoffrey de Havilland Jr., with Chief Engine Installation Designer John Walker alongside him. The takeoff was described in the test notes as straightforward and easy. In January 1941, racing directly against a Spitfire, the prototype reached approximately 382 miles per hour, well ahead of the RAF's frontline fighter. The Air Ministry had not asked for a race. They got one anyway, and the result was hard to argue with. Mass production was authorized in June 1941. The first production Mosquito, B Mark K4, flew on the 8th of September 1941. Each aircraft, 2 Rolls-Royce Merlin 21 engines, 2-speed single-stage supercharged, approximately 1,460 horsepower at rated boost. Top speed roughly 380 miles per hour. No armament of any kind. HistoryNet's summary of the concept captures the institutional bet precisely. The Anti-Fortress, a bomber proposed to the RAF with speed as its salvation, not guns. Number 105 Squadron at RAF Swanton Morley took delivery of the first operational B Mark IV, serial W4064, on the 15th of November 1941. By December, the squadron had moved to RAF Horsham St Faith, near Norwich, and was beginning daylight precision operations over occupied Europe. Those early missions were flown at very low level, sometimes 50 feet, sometimes lower, against industrial and port targets in France and Germany. The aircraft was genuinely fast. The early crews knew it. The institution that had been skeptical of the unarmed concept quietly accepted it. Speed as a substitute for armour was no longer theoretical. It was operational practice across two groups' entire Mosquito effort. What the institution hadn't yet fully accounted for was that the speed advantage had a ceiling. A specific ceiling, measured in feet above the English Channel. The challenge arrived on the other side of the Channel in the summer of 1941. In June 1941, the Luftwaffe accepted the first 100 production Focke-Wulf FW-190A1s. The second Gruppe of Jagdgeschwader 26, 2 Jagdgu 26, received them almost immediately, transitioning from the Bf-109E. By August 1941, 2 Jagdgu 26 was flying combat missions with the FW-190A over northern France, Belgium, and the English Channel. By September 1941, it was fully equipped. The rest of the Geschwader followed Gruppe by Gruppe. One Gruppe, still operating Bf-109 F4s in the late summer, converting through the autumn. By June 1942, the whole of Jagdgu 26 had re-equipped with the FW-190. Jagdgeschwader 26, named after the German nationalist Albert Leo Schlageter, was formed in May 1939. It was one of only 2 permanent fighter wings assigned to the Western Front. Its operational sector covered the corridor from the Seine east to the Dutch border. Pas-de-Calais, French Flanders, Belgium. Jagdgu 2, Richthofen, held the sector west of the Seine, Normandy, the western ports. RAF aircrew called Jagdgu 26 the Abbeville Boys, a reference to the Pas-de-Calais airfields from which the Geschwader flew. The name wasn't an official Luftwaffe designation, it was a recognition. This was the unit in the intercept corridor, the one you would find between an aircraft taking off from Norfolk and any target in northern France or the Low Countries. Photographs from 1942 show FW-190s of 2 Jagdgu 26 being pushed into hangars at Abbeville Airfield in northern France. Adolf Galland, who commanded Jagdgu 26 before his elevation to General der Jagdflieger in December 1941, had flown from Odenberg in Nord-Pas-de-Calais, a base so associated with his name that German bunker records there still reference the connection. What the FW-190's arrival meant for RAF operations over northern France became apparent immediately. The aircraft proved superior in speed, rate of roll, and diving acceleration to the Spitfire Mark V, then the main frontline RAF fighter. Where the Spitfire Mark V had held its own against the Bf-109F, the FW-190A was a different problem. RAF pilots described the new fighter as able to walk away from a Spitfire in level flight and in a dive. Its ailerons were so effective that reversing a turn appeared, from another aircraft, like a flick half-roll. The change of direction was that instantaneous. The Spitfire's only consistent tactical advantage was the ability to outturn the German fighter in a sustained turn. But a pilot who allows an FW-190 to drag him into a turning fight has already surrendered the initiative. The RAF's tactical answer for fighter versus fighter combat arrived in mid-1942, the Spitfire Mark IX, with its 2-stage supercharged Merlin 61, restored competitive performance against the FW-190 in the hands of experienced pilots. Against fighters, the FW-190 problem was being managed. Against unarmed bombers at medium altitude, the arithmetic was different. The RAF's tactical trial of a captured FW-190A3, Werknummer 313, produced documented performance figures that remain the most reliable English-language primary source for the type's capabilities at that stage of the war. Maximum speed, approximately 390 miles per hour at around 18,000 feet at 1.42 atmospheres boost and 2,700 RPM, with the test report noting the engine appeared D-rated, suggesting operational aircraft may have been somewhat faster. Rate of climb, between 3,000 and 3,250 feet per minute up to 18,000 feet under maximum continuous climbing conditions. The RAF test conclusion, written in the precise language of a tactical assessment, was unambiguous. The FW-190 is undoubtedly a formidable low and medium altitude fighter. Its performance fell off sharply above approximately 22,000 feet. The Bf-109G remained the Luftwaffe's primary high-altitude interceptor above that ceiling. Below it, the FW-190A was the relevant threat. German specifications for the A series placed maximum speed near 405 to 408 miles per hour at approximately 20,000 feet. The Mosquito B4's performance at medium altitude in operational configuration was lower than the figures most commonly cited for the type. The headline numbers, the 400 miles per hour figures in wartime advertising copy and post-war histories, derive mostly from high-boost test configurations or later marks with more powerful engines. For the B4 in two-group service, at standard early war operational boost for the Merlin 21, approximately plus 9 pounds per square in, medium altitude speeds were likely in the 360 to 375 miles per hour range between 12,000 and 18,000 feet. One RAF trial at plus 16 pounds per squared in, above the standard operating setting, produced 364 miles per hour at 12,500 feet. At plus 18 pounds per squared in medium supercharger gear, tests showed 393 miles per hour at 13,800 feet. The high-altitude picture was genuinely different. Above 25,000 feet, the Mosquito B4 in full supercharger gear carried a real speed advantage over the FW-190A, which lost performance sharply above 22,000 feet. De Havilland had built a high-altitude aircraft. The problem was that 105 Squadron's missions didn't always happen at high altitude, and the routes to and from targets crossed the medium-altitude band, where the FW-190A peaked. At approximately 18,000 to 20,000 feet, the FW-190A's documented maximum speed of 390 to 408 miles per hour either closely matched or exceeded the Mosquito B4's realistic operational speed at standard boost. The Mosquito still had options: agility in certain regimes, the ability to exploit weather and altitude, and a pilot who managed his energy correctly had a chance to find the margin. But the comfortable numerical advantage the design premise had assumed, the margin that justified leaving the guns off entirely, was no longer automatic. It had to be found under pressure. The FW-190's climb rate of 3,000 to 3,250 feet per minute at 18,000 feet also exceeded the Mosquito B4's climb performance, which meant an FW-190 with an altitude advantage could convert that into a diving attack without needing to overhaul the Mosquito in level flight. The aircraft didn't need to chase a Mozzie across 50 miles of occupied France. It needed to be above it, and close enough. Put two aircraft on the same heading, FW-190 3 miles back, closing from the stern. At 390 miles per hour, pursuing 370 miles per hour, the closure rate is 20 miles per hour, roughly 29 feet per second. At 300 yards starting separation, the FW-190 is in effective cannon range in approximately 30 seconds. That is 30 seconds for the Mosquito crew to recognize what is happening, push the throttles further, and find speed the aircraft may not currently be producing at standard boost. 30 seconds with no rear gun, no armor, no third option. If the Mosquito is doing 380 miles per hour and the FW-190 is doing 405 miles per hour, that margin compresses to roughly 25 seconds. The word the two-group operational record chose for what happened when the margin held is specific, and that word matters. This is where the gap between the design premise and the operational reality opened. 2 July 1942. Number 105 Squadron launches against the submarine construction yards at Flensburg, Germany. A long-range penetration for aircraft carrying no defensive weapons. 2 B-4s don't return. The Caspia serial database records DK-294 as failed to return, Flensburg. DK-298, flown by Wing Commander Alan Robertson Oakeshott, DFC, with his observer Vernon Frank Evans, Traherne, DFM, is intercepted by an FW-190 and shot down. Both men are killed. The German unit responsible isn't identified in the available sources. What the record confirms is the type. An FW-190A caught and destroyed a Mosquito B-4, the aircraft specifically designed to be uncatchable, and destroyed it at medium altitude over the German coast. Oakeshott was the squadron's commanding officer. A wing commander does not fly routine sorties. The Flensburg raid was considered important enough to send 105 Squadron's most senior aircrew. The loss didn't produce panic, but it confirmed what the performance data implied in arithmetic. The FW-190A could catch a Mosquito B-4 if the intercept geometry was right and the Mosquito was at standard boost. 29th August 1942. 105 Squadron B-4s attack the industrial target at Pont-Aventin in northern France, inside JG-26's intercept sector, well within range of the Abbeville airfields. FW-190s attack head-on and then turn to press stern attacks. The Mosquitoes accelerate. The secondary record of that engagement, traceable to Wooldridge's account of two groups' operations and reproduced in the operational history of the Mosquito, describes the Mosquitoes using their speed to outpace the 190s. Not escaped from, not outran, outpaced. The aircraft pulled clear. The crews returned. But the word chosen to describe the escape carries specific weight. Outpace is what you say when the result wasn't in doubt, but the margin was fought for. 19 days later, on the 19th September 1942, the same sources describe 105 Squadron pilot DAG George Parry shaking off BF-109s after a daylight penetration sortie, and the word used there is different. He was able to outrun them. Against the BF-109, outrun. Against the FW-190, outpace. The language suggests the margin against the BF-109 was larger, more automatic. Against the FW-190, the word became smaller, more qualified. Something was being measured in the choice of verb, even if the person choosing it wasn't doing so consciously. One aircraft from the Pont-Aventin formation didn't make it home. Caspia records DK-303 as accident crash, ditched 9 miles off Dungeness, Kent, on the 29th August 1942, the return leg. Whether it was damaged in the engagement over France or encountered a mechanical problem on the way back across the Channel, the record does not specify. The FW-190s were outpaced. 1B-4 still ended up in the water. Against this backdrop, the two squadrons completed their move to Marham. RAF Horsham St Faith was being transferred to the USAAF in September 1942, as the Americans built out the 8th Air Force infrastructure across East Anglia. No. 105 Squadron packed and moved in late September. No. 139 Squadron made the same transfer on the 29th September 1942, confirmed independently by the Wartime Memories Project, the IBCC Digital Archive, and the 139 Squadron Wikipedia article. Both units now occupied the same permanent station in West Norfolk, 9 miles southeast of King's Lynn. Both equipped with Mosquito B-4s, both assigned to No. 2 Group, Bomber Command, for low-level daylight precision bombing across occupied Europe. The Caspia database records B-4s of 105 Squadron taken on strength at Marham from the 12th October 1942. The target list from Marham is a record of exactly what those crews were flying into. 25th September 1942. 4 105 Squadron B-4s attack Gestapo headquarters in Oslo from 100 feet. DK-296, the lead aircraft, flown by squadron leader Parry, the Caspia entry notes it plainly, attacked by FW-190 fighters but evaded them. 6 December 1942. Operation Oyster. Both 105 and 139 squadrons in the two-group low-level daylight attack on the Philips Electrical Works at Eindhoven. 30th January 1943. 3 105 Squadron B-4s over Berlin at exactly 11 o'clock, timed to knock Goering off the air mid-speech. 27th January 1943. The Burmeister and Wayne Diesel Works in Copenhagen. 3rd March 1943. Molybdenum mines at Knaben, Norway. Every route across northern France, Belgium, the Low Countries and Denmark crossed or skirted JG-26's intercept sector. A 139 Squadron pilot's recollection, preserved in the unit's Pathfinder history, is characteristically direct. When 139 Squadron converted to the Mosquito, it was at first based at Marham and involved in low-level daylight raids. 2 crew, no guns. Abbeville on the route to almost everything. That is the pressure that produced Francis Rodwell Banks. His full name matters here because a number of secondary accounts, online videos, social media posts, popular histories, call him Roderick Banks. That is a secondary literature error. The confusion is understandable. His nickname was Rod, derived from his middle name Rodwell, and the step from Rodwell to Roderick requires almost no imagination. But his name was Francis Rodwell Banks, born 22nd of March 1898, son of Bernard Rodwell and Frances Emily Banks. His papers are held at the Churchill Archives Centre in Cambridge, reference code GBR 0014/FROB, dated 1908 to 1988. He died on 12th of May 1985 as an Air Commodore, CB, OBE, MIM Mech E. Banks had spent his career at the intersection of engine performance and fuel chemistry. He entered the Royal Navy in 1914 at 16 and commanded coastal motorboats before leaving the service in 1919 after duty in the Caspian Sea during the Russian Civil War. By 1925, he was Chief Experimental Engineer at Peter Hooker Limited, working on a 1,500 horsepower airship engine. He joined the Ethyl Gasoline Corporation's export division in 1930 developing high-octane additives for aero engines across Britain and Europe, work that brought him into contact with every major military air force and engine manufacturer on the continent. His status was such that he was invited to develop the fuel blends for Britain's Schneider Trophy entries in 1929 and 1931. The high-octane formulations that allowed the Supermarine S6B to extract previously impossible power from the Rolls-Royce R engine. In 1931, he was called in to diagnose the backfiring problems that had killed 2 Italian test pilots flying the Macchi Castoldi MC-72 seaplane. The aircraft was powered by the Fiat AS6, a 24-cylinder engine producing 3,100 horsepower that ran perfectly on test stands and exploded in flight. Banks identified the cause. The Fiat engineers had not accounted for the ram effect of a 400-mile-per-hour slipstream on the intake fuel mixture, which leaned the charge below what the engine could tolerate under compression. He modified the intake design. The MC-72 went on to set the absolute propeller-driven world speed record in 1934 at 440.68 miles per hour, a record still unbroken. The Royal Aeronautical Society gave him the Taylor Gold Medal in 1934 for his paper on ethyl additives. This was Banks's characteristic skill, finding the gap between where the documentation said an engine's limits were and where those limits actually sat, and then working precisely in the space between those two numbers. With the coming of war, Banks entered the RAF Volunteer Reserve as a junior officer, assigned to the Aeroplane and Armament Experimental Establishment at Boscombe Down. Lord Beaverbrook, the Minister of Aircraft Production, had been briefed on his previous work and gave him special troubleshooting authority. He would eventually serve as Director General of Engine Production and Director of Engine Research and Development, reaching Air Commodore. Accounts of what happened at Marham in late 1942 describe Banks working on 105 Squadron's Merlins and applying a modification to the boost settings outside official approval channels. According to aviation historian James Fennell's account, the commanding officer of 105 Squadron, Squadron Leader Peter Channer, became aware of what Banks was doing, flew the first modified aircraft himself, achieving more than 400 miles per hour in level flight, and then flew his next operational mission, reportedly evading 2 FW-190s that the unmodified aircraft might not have outrun. Word moved through the squadron quietly, then through 2 groups' Mosquito fleet. Banks trained a network of fitters who applied the same modification to other aircraft, one by one. Nothing was written. No Rolls-Royce authorization had been sought. No official modification order existed. Station commanders reportedly cultivated productive ignorance of the specifics. The modification reportedly spread because the results were visible. Modified aircraft were returning from engagements that unmodified ones were losing. These accounts are secondary narrative sources, operational histories, the Fennell thread, documentary summaries, rather than confirmed primary documents. The Banks papers at the Churchill Archives Centre haven't been exhaustively examined in the sources available here, and the Squadron Orbs in the Air 27 series at the National Archives haven't been directly quoted on this specific modification. What the accounts describe is credible, given Banks's documented expertise in exactly the fuel chemistry and boost limit questions the modification addressed. The history is presented at the confidence level its sourcing supports. Established operational narrative, not a verified primary document. To understand what Banks reportedly changed requires understanding how the Merlin manages power. The Rolls-Royce Merlin in the Mosquito B4 is supercharged, not turbocharged. This distinction is fundamental and frequently confused in popular accounts. A turbocharger is exhaust-driven. Hot waste gas from the cylinders spins a turbine that drives the compressor. The Merlin supercharger is mechanically driven directly off the crankshaft through a gear train, spinning continuously at a fixed ratio to engine speed, regardless of throttle position. The compressor forces air into the inlet manifold at above atmospheric pressure. That excess pressure, expressed in pounds per square inch above atmospheric, is the boost figure. More boost means more air delivered per intake stroke, more fuel required to match it, more combustion energy released per cycle, more power at the crankshaft, more speed at the propeller. The boost controller governs that figure. Its core component is an aneroid capsule, a sealed, deformable bellows whose interior holds a calibrated reference pressure. The capsule deforms in response to the difference between actual manifold pressure and its internal reference. A calibrated spring sets the reference load, the amount of force required to compress the capsule to a given deflection determines what manifold pressure the controller treats as its target. The controller monitors that balance through a valve linkage, backing the throttle off when manifold pressure exceeds the target, opening up when it falls below. In normal operation, the engine holds the target boost almost automatically across a range of altitudes and throttle positions. The spring determines the target. Shift the spring's preload or alter the capsule's reference position relative to the valve linkage, and the controller holds a higher target manifold pressure before it begins backing off. The aircraft produces more power. It goes faster. The certified limit existed because there is a hard upper boundary to how far manifold pressure can go before detonation occurs. Detonation isn't rough running, it's compression ignition, the fuel-air charge in the cylinder igniting spontaneously from heat and pressure before the designed spark event, before the piston has reached the correct position. When it happens, multiple combustion wavefronts propagate simultaneously inside the cylinder, generating pressure spikes that can destroy piston crowns, crack ringlands, rupture cylinder heads, and seize the engine in seconds. The boost limit was calibrated to the octane rating of the available fuel. High-octane fuel suppresses detonation by resisting spontaneous ignition under compression, which is why the highest boost wartime operations required 100 or 150 octane grades. The Merlin 21 certified limit reflected where, at the grade standard for 1941-1942 operations, the engine's structural reliability required the boost to stop. Temperature and mechanical stress were cofactors. Detonation was the primary failure mode the limit guarded against. Banks reportedly had sufficient understanding of the relationship between fuel chemistry, compression ratio, and the actual detonation threshold to judge where the genuine ceiling sat versus where the conservative certification line had been drawn. He reportedly found the gap and moved the aneroid reference to exploit it, not by ignoring the detonation risk, but by operating within its actual physical boundary rather than the boundary the certification documentation had specified. The official limit was where the paperwork said to stop. The physical limit was somewhat higher. Banks built modifications in the space between those two numbers. The accounts cite a speed gain of roughly 25 to 30 miles per hour over the approximately 380 miles per hour standard baseline, placing modified aircraft around 405 to 410 miles per hour at altitude. These figures appear in secondary narrative sources and haven't been confirmed against Bomber Command operational research documents. They are presented as the claimed differential, not a measured figure from a contemporary trial. The significance of even the conservative end of that range becomes clear against the documented FW-190A performance. At 18,000 feet, the captured aircraft test placed the FW-190A3 at approximately 390 miles per hour. And with an apparently D-rated engine, operational aircraft were likely faster. At optimum altitude near 20,000 feet, German specifications placed the A-series at 405 to 408 miles per hour. An unmodified B4 at standard operational boost, perhaps 370 to 380 miles per hour at that band, was inside the FW-190's speed envelope. A modified B4 at 405 to 410 miles per hour sat at or above the FW-190's documented maximum. The arithmetic follows directly. Two aircraft on the same heading, FW-190 300 yards astern. At 380 miles per hour versus 405 miles per hour, the gap opens at 25 miles per hour, roughly 37 feet per second. The FW-190 is getting further away. Reverse those numbers: 380 miles per hour Mosquito, 405 miles per hour FW-190, and the FW-190 closes that 300 yards in approximately 25 seconds. No rear gun, no armour, no option except the throttle. Banks's modification reportedly moved 105 Squadron from one side of that calculation to the other. Loss rate figures from the narrative accounts place modified 105 Squadron aircraft at approximately 0.33% per sortie against approximately 0.6% for standard configuration Mosquitoes. These figures come from secondary sources and haven't been confirmed against Bomber Command operational research statistics. They are presented as claimed, not verified. But the direction they describe, modified aircraft surviving at nearly twice the rate of unmodified ones, is directly consistent with what the performance differential implies. An aircraft that shifts from inside the FW-190's speed envelope to outside it would be expected to produce exactly this kind of survivability gap in tail-chase interceptions over northern France. Some 105 Squadron crews were attending to their airframes at a different scale as well. Sanding surfaces, polishing the wooden fuselage and wing skins to reduce parasite drag, hunting fractions of a mile per hour in an aircraft where fractions mattered. The practice is documented across RAF Mosquito units of this period, and it was consistent with de Havilland's construction philosophy from the beginning. The smoothness of the wooden finish was integral to the aerodynamic design. The Mosquito was partly fast because it was smooth, and keeping it smooth was engineering, not superstition. But polishing changes the drag on the finish. Adjusting the aneroid reference changes the maximum power the engine is permitted to produce. Banks reportedly changed the sealing. The polishing changed the paint. According to the Fennell account, in early 1945, a Rolls-Royce chief engineer named Ernest Hythe arrived at Marham unannounced, found Banks working on a Merlin in the workshop, and spent 3 hours examining what had been done. Hythe reportedly concluded that the modifications were consistent, well-considered, and systematic. Not rough tinkering, but applied engineering that had been producing results Rolls-Royce's own conservative ratings had not anticipated. 3 weeks later, Rolls-Royce reportedly issued a technical bulletin authorizing boost modifications under specified conditions, effectively ratifying what Banks had been operating for more than 2 years. Whether that bulletin covered exactly the 105 Squadron modification in its specifics isn't confirmed at primary level in the available sources. What the accounts agree on is the direction. Institutional certification caught up with operational practice. The Mosquito went on to Berlin in January 1943 and disrupted a Goering speech. It flew Eindhoven, Copenhagen, Oslo, Knaben, and dozens of targets across occupied Europe from Marham and the bases that followed. Over the full course of the war, the Mosquito dropped more explosives with fewer losses than any other bomber type in RAF Bomber Command service. Goering himself, raging at German aircraft manufacturers after the January 1943 Berlin raid, said it directly. "It makes me furious when I see the Mosquito. I turn green and yellow with envy. There is nothing the British don't have. They have the geniuses, and we have the nincompoops." The aircraft he was raging about was, according to the accounts of the modification, running at +20 in every Merlin rather than the number on the specification sheet. The Focke-Wulf FW-190 of JG-26's Abbeville wing didn't invent that setting. Banks created it. But the FW-190A at medium altitude, flying from Abbeville and the Pas-de-Calais airfields, operating in the intercept corridor between RAF Marham and every major two-group target in northern France and the Low Countries, created the operational pressure that made the certified Merlin boost limit feel inadequate for the job 105 Squadron was flying. The margin that justified building an unarmed bomber had been real. On 25th of November 1940, W4050 beat a Spitfire by a clear margin over Hatfield. Geoffrey de Havilland had not written a dishonest letter. The promise was genuine. But by the summer of 1942, the Abbeville wing was flying an aircraft that peaked at 405 to 408 miles per hour at 20,000 feet, and the Mosquito B.4 at standard operational boost wasn't reliably above that number at the altitudes where 105 Squadron's work was done. Outpaced was the word the two-group operational record used to describe Pont-à-Vendin. Not easily escaped, not left far behind. Outpaced. That is the word you choose when you are measuring the gap in feet per second, not miles, when the crew found the margin rather than assumed it. The Mosquito's daylight reputation was never pure magic. It was a margin, and the Abbeville FW-190 had compressed that margin to cockpit-felt seconds at the altitude where those crews worked. That is why every one of those Merlins reportedly ended the war at +20 instead of the number on the spec sheet. Not ambition, arithmetic. Subscribe for more stories like this.